Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you're all doing okay. I'm a little tired, not just because I'm not a morning person, but I haven't been sleeping well, as I think I told you guys. For no reason. Okay, everything looks good here. Yeah, so the thing is, if you're a person like me, one thing you learn that I don't know if anyone of you is going through this, but if you are, normally you have the temperament where you're like, everything's cool, everything's going to be okay. I mean, don't get emotional, think logically about it. If you're one of those kinds of people, what you realize is that usually, not always, there might be medical conditions, but if you don't sleep well when there's kind of no reason for you not to sleep well, that's anxiety. That's what you learn. Like some people are anxious when they're awake and they're conscious, and some people aren't, like me. And it's like how you know when you're anxious about something is it sneaks up on you. It messes with your sleep because your subconscious mind is like all freaking out about stuff. Oh my God, the sky is falling, and then your conscious mind has this identity where it's like, no, we don't freak out. Everything is okay. So when you go to sleep and your conscious mind is resting, that's when your subconscious mind runs amok. It's like, yeah, really messes with your sleep. So yeah, so so that's how you know you're anxious if you're not usually an anxious person. Some people are anxious while they're awake. I can't imagine that. That's rough, buddy. Okay, let us get things started because we have a shorter time than usual today. If you're one of those people who are anxious while you're awake, you need to start meditating or something. It's something you want to try to get under control. But it's finals week. Everyone's anxious. Okay. All right. So let's actually get into this. So where were we? We've been talking about polar coordinates. As I mentioned, it's a different way to locate things in space based on a distance from the origin and an angle with a positive x-axis. So you can move to an angle, extend a certain distance, and whatever point you hit when you hit that distance, that is what the polar coordinate is kind of pointing you towards. Difference between polar coordinates and rectangular coordinates, the kind of coordinate system we're used to using, is that polar coordinates do not have a unique address because angles can be coterminal. You can have many different angles that hit the same point, as well as we're allowed to have negatives in terms of our distance function. And we're also allowed to have negatives in terms of our theta. And both of the times, these negatives indicate a change in direction. So instead of going towards the angle, you move away from the angle. Or if the angle is negative, you move clockwise instead of counterclockwise. So that means you have even another set of possible addresses with either positive or negatives in the first coordinates and corresponding angles that are by magnitude, they're different, but in terms of location, they're the same. And that gives you an infinite number of addresses for any one particular point. However, anyone would know they all point to the same location. And so sometimes we'll standardize things and we'll say, okay, only pick angles between 0 and 2 pi so everyone is on the same page without having to convert anything. We learned some equations of how we can switch between coordinate systems, because sometimes if you have a very powerful mathematical machinery, you do want to be able to translate to and from less advanced mathematical machinery, because you can solve problems that you otherwise couldn't solve. And we actually did some examples where we were doing the conversion, where we are converting from polar to rectangular in this case. And we did some convergence from rectangular to polar. There are nuances when converting from rectangular to polar because you can have positive or negative R values usually because the R equation comes from a squared equation. And of course, your angles, if you add 2 pi and blah, 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 you can do that. So one, you can either find a particular point, any point that you want to find there, or two, you can actually mention it in more general terms. And of course, when you are on in like a scenario where there's multiple choice, then you should be able to recognize the answer no matter what form I put it in. So if you calculated this and you see this as a multiple choice answer, you should recognize that, yeah, those are the same thing. Because if I add 2n pi to my pi over 4 answer, it's not going to make a difference. So you would be able to recognize the answer in either way. So as for the kind of answer that you would give in the first place, that is going to be based on the instructions of what I asked for. We also looked at, and this is very important, it's going to be very important, even more important going into multi-1 and multi-2, by the way, and some courses beyond that if you're going to do complex analysis or anything like that. Being able to sketch anything that's calculus-based that you're doing in 3 dimensions or less, sketching is going to be very, very important. So we do want to know how to describe regions, how to sketch regions, and how to describe them in a particular coordinate system. We saw that the benefit of the polar coordinate system is that, one, it can describe circular regions a lot more efficiently than it would than a rectangular coordinate system. So in a polar coordinate universe, when it describes a circle in our XY universe, it's actually like describing a rectangle in the polar coordinates universe, which is a lot easier to deal with on multiple levels. So we went through some examples where we were describing regions and talking about them in polar coordinates versus rectangular coordinates. And we can already see how rectangular coordinates, they're all more complicated than the polar coordinates. Like, I think every single polar coordinate situation I did here, it's like it's a kind of rectangle in the polar coordinate universe. And it's the variables just went between constants, right? And look at these crazy shapes that we're doing, right? And different slices that we're doing. And by the way, I think I changed one of these, so I should probably mention. I think I changed one of these. I think it was this one. I rewrote it because I didn't like how I wrote it in the last night. So when you see the notes, make sure that you make this change. So you can mark that on your notes and say, oh, it should be updated. Because I don't think going straight from x equals -3. I mean, what I wrote was technically correct, but I think you'd want to separate it. Like, you let the -3 to 3 happen here, and you let the -1 to 1 happen there. And yeah, that's all we spoke about. One thing that you're also going to want to be able to do is recognize what graphs in polar would actually look like. So you should be able to see an equation in polar coordinates and identify what kind of graph it is. And sometimes the thing is with polar coordinates, because we can represent simple equations, so complicated situations relatively easier than in rectangular coordinates in many scenarios, we can actually get very complicated looking graphs that are not even functions, relatively easy from a polar coordinate setup. These graphs, though, we are not going to do. I left them here just show you what you're missing. But I'm not going to cover them because, well, mainly because I think it's a waste of time. This is not, I don't know many people who have to sketch polar graphs outside of a Calc 2 class. I've actually never met another person who had to sketch a polar graph outside of a Calc 2 class. So you learn this thing in Calc 2 and you literally never use it again. Calculus with polar coordinates, we are going to be skipping this as well, not because it's useless, but because there are a lot of people who would use this. However, it's exactly the same theory for calculus with polar equations, with parametric equations. So your dy dx, you'll find it by dy d theta over dx d theta. So it's just like you're applying your knowledge of calculus with parametric equations, except it's going to be a little bit more annoying with polar coordinates because now you're forced to use specific trig functions. And of course, when you're doing trig functions, it can get annoying because you have reference angles and all that stuff. But in theory, everything works out exactly the same as it did when I spoke about calculus with parametric coordinates, parametric equations. So if you're ever going to be in a situation in the future where you have to do calculus with polar coordinates, which in multi-1 and multi-2, you are going to have to be doing that to some degree, though you're usually not going to be differentiating things. You're usually going to be integrating things. But if you go, a lot of your physics courses and engineering courses will also have you doing calculus in polar coordinates. But as I said, technically you wouldn't be learning anything new at that point. You'll just be applying techniques you already know to a very specific scenario. So I also think it's kind of a waste of time to do this in Calc 2 because I'm not teaching anything else. Here, areas and lengths in polar coordinates, same thing. You use the same strategies. Arc length in polar coordinates, use the same strategies. It's x prime squared plus y prime squared square rooted. It's all the same, just that when you have trig functions, things work out a little bit different. So overall, I'm going to skip these because I'd rather get to some more interesting things. And these are just going to be things that they're just really, at the end of the day, going to be computationally annoying, and you're not really going to learn anything from doing it. You know, contrary to popular belief, math people don't give you annoying homework and stuff just for the hell of it. Like if I ask you to do something that's annoying, there's a reason for it. I'm not going to do something just because it's annoying. So these graphs here, relatively simple functions in the rectangular universe. That's just a sine function and a cosine function. These are all just sines and cosine functions shifted. But in the polar universe, they give you all these wonderful shapes. So I thought I would just show you guys what it would look like so you don't feel like you're missing out too much. If you are interested in these things, I would say wait until the end of the semester after the final exam for this class. I have taught these things in past and it is on video, so you can go and watch those and learn about this stuff if you want to. But as for right now, I'm not going to test you on them, so ignore everything in this section right here. Ignore the calculus of polar coordinates. One thing I do want you to know, which we're going to get to now, is just how to talk about graphs, basic graphs, and just being able to convert between graphing ideas between the different universes. That's going to be important in the future, and it's something that it's a skill you have to learn and practice. Okay, big introduction and recap. Let's actually get into it because we don't have a lot of time. So let's hope my fingers are working. All right, so r equals 1. Maybe I'll take some suggestions here. What do you guys think that is? R equals 1, based on what you know about polar coordinates. What would you think that graph is?
A circle?
It's a circle, right? Now, there are a couple ways you can come to that realization. So one, you can know conceptually this says distance from origin is always 1. And then you ask, what kind of curve would it be that no matter what direction I look in, its distance from the origin is always going to be 1? Well, a circle. Specifically, a circle of radius 1 centered at the origin. There is a formulaic way to do this as well. Is to remember that your r squared is equal to x squared plus y squared. And so if you have r equals 1, that's the same as saying r squared equals 1, and that's the same as saying x squared plus y squared equals 1. And so either way, you would be able to conclude that you get to a circle of radius 1. Okay, yeah. So if you see r equals 1, it's another way of writing x squared plus y squared equals 1 in rectangular. So that is a circle. What do you think theta equals pi over 4 is?
It's just a line.
It's a line. Do you know what line? Can you tell me the specific line? Like last time it was suggested that this was a circle. A more specific answer is it's the circle of radius 1 centered at the origin. So you say this is a line. Do you know the specific line?
The angle from the x-axis, or I'm not sure how you call it, is pi fourths.
Right. So that's like 45 degrees.
Yeah.
So what line do you know behaves like that?
Would that just be y equals x?
That's just y equals x, right? And so again, conceptually, basically you're in a situation where the angle with x-axis is always pi over 4. So you end up in this situation where you have an angle of pi over 4. And you're talking about all points that lie at that angle. Of course, you could go in the opposite way. So this is what you would get if your r is negative and your angle is pi over 4. And this is what you would get if your r is positive and your angle is pi over 4. Ultimately, this leads to just the line y equals x. Conceptually, I think is a faster way to do it, but you should be able to justify anything by formula as well. So let me show you the formulaic way. Formulaic. Pretty much you know that theta is equal to tan inverse of y over x, which means that if you have pi over 4 equals tan inverse of y over x, you know what that means. It's that your y over x must be equal to 1. And so you would have to get y equals x. Okay, so a couple ways to see that there. Getting a little bit more challenging. R equals secant theta. Ideas?
Could this be a trig identity?
Trig identity for what?
Secant squared equals tan squared plus 1.
Okay, so you're thinking of squaring both sides, you get r squared equals secant squared, and then, yeah, but how would you write r squared as tan squared plus 1? Yeah, that's a little bit harder. I guess you could square both sides and try to force that identity in there. And then something like you'd write tan inverse of y over x, but that's working too hard. Anyone see another way? I know it's early and I'm asking you guys to think. I apologize, but I do want you guys getting used to this idea of how to think in polar coordinates. And again, I mentioned 2 ways in which you can come up with the answer. I don't think the conceptual way is going to help much here, to be honest. These formulas that I asked you to memorize, right, says right here, memorize. When in doubt, you kind of want to go back to those guys. So look in your notes or take a picture right now, and because that's what's going to help you. And this is a lot of the idea behind mathematical formalism. When our intuition fails us, our math logic and formulas save us. Okay, so that's what people mean when they talk about things like, oh, math is really about how to think logically. That's what they mean, kind of. Pretty much any mathematical statement, there's an intuitive statement behind it, but the math formalism really helps make that concrete. So you'd probably want to go the more concrete route here. So based on those formulas, any ideas? Anybody out there? Is there anyone with no idea what to do?
Yes.
Okay, all right, so she answered that. Okay, all right. Throw out any idea, no matter how wacky it sounds. Tell me something. What are you thinking? You see R equals secant. What are you thinking?
I don't know how it could be helpful, but could you rewrite it as 1 over cosine theta?
There's an idea. Now, why did you decide to write it as 1 over cosine theta?
Because the other trig identity we tried didn't work.
That's why? That is
Quite honestly, yes.
okay. That's not bad, by the way. So yes, a lot of times, a lot of mathematical discoveries actually comes from guessing. And when those of you who want to do a course like differential equations, you're going to realize it's very strange, but you're going to be spending a lot of time. Maybe the answer looks like this. Oh, that worked. Okay. So guessing is not bad. I would suggest here, though, that there's another reason. There's actually a very concrete reason why I would want to write this. And again, the formulas are the guide. So if we go back to the formulas, what do we notice about the formulas in terms of trig functions? Tell me something obvious. I'm not asking a trick question here. When it comes to trig functions and you're looking at these formulas, tell me, what do you see? And even if it sounds obvious, just say it, because I am looking for the more obvious answer.
Well, if we multiply by a cosine now, we have our cosine theta is x, so x is 1.
Right, that's true. That's not the obvious fact, though, that you're thinking of the problem, which, yes, you just solved it, okay? But here's the obvious thing that I want you guys to learn when looking at formulas. if I have a set of formulas that tells me about some sort of mathematical theory or idea or something, and I'm in that universe and I'm looking at an object that doesn't conform to any of the formulas that I know set up this universe, one thing you're going to want to do is try to convert that new formula to be in the language of the equation that set up the universe. So I look at these equations. Here's something I notice. Cosine is there, sine is there, and a tangent inverse is there. None of the other trig functions are there. There's no secant, there's no cosecant, there's no cotangent, which means if I'm in a situation where there are trig functions and I don't know how to deal with it, then it's probably best that I convert to one of the trig functions that are here, right? So I would think to convert secant to 1 over cosine, not because it was randomly a guess, although you could get a lot of places there, but specifically because there is no secant in my original set of formulas. However, I can write secant very easily in terms of cosine, and there's a cosine in my set of original formulas. So that's why we would guess that step. And so now, yeah, as Stephen mentioned, now you can multiply both sides by cosine, and now you have r cosine theta. But we know what r cosine theta is. That's just x. So this is actually a fancy way of writing the line x equals 1. This brings up something else that I don't want to dwell on too much, but yeah, this is the line x equals 1. So now we're seeing the dark side of polar coordinates. Well, not really, but here we're noticing something. There's a contrast that you can make. Notice that when I was looking at circular regions, polar coordinates were very efficient, very nice to describe things. Here I'm looking at something that has no curve in it whatsoever. It's as far from a circle as you can get, literally. The endpoints don't even touch each other and they never get closer together. And it's just they're going in opposite directions. And now the polar coordinate way of describing this is a little bit more complicated. I mean, in the polar coordinate universe, this straight line is essentially like a graph with asymptotes. This should be one versus the other. Right? So if I'm dealing with a straight line, probably I want to stick to rectangular coordinates, right? Because the polar coordinates actually makes this a little bit more complicated. And that's something that you're going to explore a lot more in Multi-1. Normally, if you ever want to know, why would I switch to polar coordinates? It's usually going to be because there's a region that is circular that you want to deal with. If there's a region that is covered by straight lines, you probably want to stick to rectangular. Okay. Now, I don't want to dwell on that too much because one, I want to hype up polar coordinates, so I'm going to tell you all the good things about them and not stress the bad things about them. But just in the interest of fairness and comprehensiveness, I do want you to be aware that there are some situations which polar coordinates can make things a little bit more complicated. However, you can convert it to simpler situations by paying attention to those formulas. Based on what we learned there, I have the curve r equals 2 cosine theta. What do you think we can do here? What is that? And I don't want to spend any time here, too much time here. Is this the last example? Yes. So yeah, just throw out whatever idea is in your head and we'll move on. Because no matter what, even whether it's right or wrong, we will learn something, right? You'll learn how to look at it in the future. So what I'm interested in is if you saw this on a test and you didn't know what to do, what would you guess, right? So that way I can kind of tell you what a proper guess might be or how close you are to guessing in the right direction. That's also something important. So whether you think you know the answer or not, just tell me what's on your mind. Let me guide you, grasshoppers. What are you thinking? And again, I'd also appreciate if you guys have your cameras on so I don't feel like I'm talking to myself. No, because when there's silence and I'm not seeing anybody, it's morning, right? Joe, you don't want to see me right now. Really, like my hair is like this. I'm half asleep in my pajamas. Don't want to see me before my coffee. Ideas, anything. Go on, shoot them.
This is probably incorrect, but could you say
It doesn't
that
matter.
inverse cosine of r over 2 equals theta? Would that get us anywhere?
No. Okay, and
Figured as
here's the
much.
more important thing. Why would that not get us anywhere? So I'm very glad you said that. So that was a guess. Not the guess I think is the one you should go with, but why was that not the guess that you should go with? Because again, go up here. Are there any inverse cosines in this set of equations? Sure, we have this one. And that's an extra set of equations that I just wrote down on the side when the tangent one gives us trouble, which happens whenever our point is located on the y-axis. But that's not one of the main equations. And second of all, that helps us find theta, which I don't know if that's going to help us here, just being able to find theta. Although, in a roundabout way, it probably could, but I'm actually not even interested to try because I think I have to work a lot harder than I want to. So I wouldn't guess in that direction because it's either going to lead nowhere or you're going to have to work really hard. So again, looking at these equations right here, okay, these are your guides. These are the guides that tell you about how do I describe the rectangular world in polar coordinates, right? So this is your base right here. So look at those again and try to find a way to somehow finagle what we have into one of the forms that you're seeing here. Does anyone see it? This one's a little bit harder to come up with the idea, but it's actually a very simple idea. So here you notice I have a cosine theta, which does appear in my formulas. If I look at my formulas, let me stop scrolling up and down. So I see this, I know my formulas. I know that x is equal to r cosine theta, y is equal to r sine theta. I know that r squared is equal to x squared plus y squared. I know that my theta equals tan inverse y over x, right? So I know all these formulas. And these guys should always be in the back of your mind or the front of your mind.
Can we multiply by an r on each side and then get our cos theta to be an x on the right side?
Ah, yeah, now you're seeing it. Okay, so yeah. Okay, when back of your front or the back of your mind when doing or dealing with polar coordinates. Yeah, you guys got it. I know it. I believe in you guys. Okay, so yeah, Notice that there's a cosine here, and I do have a cosine here in my formulas, but it's missing the r. So my idea would be, could I put an r in here? And you would now ask yourself, well, how would I be able to put an r in there? Well, it's an equation. I can multiply both sides of that equation by the same thing, right? So like I said, it's coming up with the idea. It's a little bit complicated if you've never worked with this before, but once you see the idea, you realize, oh, that's actually, it's a pretty simple idea. So I would multiply both sides by r. And I multiply by r because of this equation. Now what you notice is that I have an r squared and I have an r cosine theta. So now I'm going to use the suggestion by Hannah in the chat, and I can convert the r squared to x squared plus y squared, okay? Because this thing looks very complicated to me in polar coordinates. I don't even know where to start. So let's convert back to rectangular. What kind of curve is that? That's right, it's a circle. Okay, yes. Okay, she just, okay, so Hannah got it. Because there's no way she could have typed it that fast. So we came up with the idea together. It is a circle. Of course, it's not in the exact form of a circle. We have to do a little bit of work. So of course, we all remember how to complete the square. So that's what we would do. You can add 1 on both sides. And so this really becomes x minus 1 all squared plus y squared equals 1. So that tells you it is a circle of radius 1 centered at 1, 0. So if I have a shifted circle, I usually get something like r equals cosine or sine. And as I mentioned here, more generally, if I have r equals, say, a cosine theta plus b sine theta, I could multiply through by r. That would give me x squared plus y squared equals a times x plus b times y. And I can move these guys over. And I can complete the square. And this is going to be a over 2 squared plus pretty much a squared plus b squared over 4, I think. Yeah, so I wouldn't memorize that. Once you memorize these sets of equations, as I was talking about yesterday, there is a line between what you would memorize versus what you wouldn't. I would memorize this. Because once you have that and you have algebra skills, you can get to this if you need to. So save the space in your brain. Don't need to memorize this. Once you see this technique that I just show you, now you know how to actually get here. if you can get from one set of memorizations to another with minimal effort, it's just a little bit of algebra, you just need a little bit of elbow grease, then don't memorize everything, memorize the foundation. Essentially, yes, to answer the question. In these scenarios, are we trying to convert what's given to us into one of the four formulas? One or several. Notice that I used several of the formulas here. I used the formula for r squared and I used the formula for r cosine theta. But yes, why memorizing certain formulas is very important. And again, this goes against what a lot of people are preaching these days. So, let's teach students how to understand. And now students are taking like 3 pages to add 2 numbers in elementary school. Or kids are just going to grow up hating math more because they're like, let them understand what it means to add. No, memorize your times tables, learn how to add by rote. Because once you know that, it frees up your creative mind to start thinking of things like, how can I morph this into that? So this thing that I have memorized, this schema I have memorized, how can I morph other things into it? Like, that's what math is about. Okay, so yeah, you know a set of formulas that will always work in your scenario. Then yeah, if you're in a situation where you don't know what's going on, like that's very complicated. I've never seen something like that before. Yeah, try to rewrite it in the language that you already understand. I already know these sets of 4 equations that I have memorized. I understand how they work, why they fit. I can convert anything into that. And I can now go from a situation where I'm totally confused to a situation where I know how to handle it. I know how to solve the problem. And that is math, right? Math is not the memorization of the formulas. That's true, but it involves the memorization of formulas. Okay, that's actually all I wanted to talk about with polar coordinates. And what I'm going to do for the rest of the time, I actually spent a lot more time on this. I spent like 15 more minutes on this than I wanted to. But what I want to spend on the rest of the time is things like this. So we got to this point and I asked you guys, what kind of curve is that? And it took a while for you guys to say circle, right? So I get it, it's okay. I'm not judging you, but you need to get to a point where you should recognize that quicker. That's going to be important in the next class as well, and in every class after this. So right now I'm going to move into something that's not even really a Calc 2 topic. It's really something that you would have learned a long time ago, but a lot of people have forgotten and they just don't remember these formulas. They're not thinking about them and they would have forgotten a lot of things about it. So that is the topic of conic sections. And again, full disclaimer, we're not going to do this in any degree of detail. I am literally going through this topic and only going to remind you about a few things that people tend to forget. The main focus here is on sketching. As you will realize in Multi-1 and beyond, being able to draw a picture of the situation, especially when you're going to learn about 3 dimensions, and it's going to be very hard for you to think in 3 dimensions because you've literally been thinking in 2 dimensions your entire lives up until this point when it comes to math. And that was hard enough. Now, when you go into Multi-1, they're going to throw in a 3rd dimension on you, and you're going to like, I don't know what's going on. The secret to knowing what's going on is being able to sketch scenarios. So sketching is very important. And it turns out to be able to sketch well in 3 dimensions requires being able to sketch things well in 2 dimensions. So you're going to have to remember how to sketch certain things. Now, in general, students do remember how to sketch things like parabolas, which is a kind of conic section. They're called conic sections because you can get them by slicing things out of a cone here. I'm not going to talk about that. I will say, just a plug here, here's a YouTube video by someone else. It's not me, but it's really cool. For those of you who learned about conic sections and circles and ellipses and hyperbolas and all that stuff, and you're like, what is the point? Here is a video that talks about some really cool applications of conic sections, which I'm not going to go into. Yeah, moving on. Most people remember parabolas. Most people don't remember what the directrix or the focus of a parabola is, and I'm not going to ask you to remember that either. So you can ignore that. But parabolas people tend to be okay with. Ellipses, not so much. Most people don't deal with ellipses every day, you're going to need to remember how to deal with ellipses, specifically how to sketch them. Ignore the foci. Same thing here with ellipses, ignore the foci. A circle is just an ellipse where the A and B are equal, right? Hyperbolas, people really forget about these, how to sketch them, what they look like. Ignore the foci and asymptotes. I'm not doing it in detail. I pretty much want you to remember, one, how to recognize when you see one of these formulas. You should be able to look at something and know, hey, that's a hyperbola. And if someone asks you, could you sketch me something? Not in great detail, but a basic sketch of a hyperbola, you should be able to do it, okay? You're going to learn about hyperboloids of 1 sheets, hyperboloids of 2 sheets. These are very complicated looking 3-dimensional figures where you can figure out what they look like and what they behave like by actually sketching 2-dimensional hyperbolas. So that's going to come up in Multi 1. And whenever you get into that section and your professor is sketching things on the board and you look over to your classmates and everyone's eyes is glazing over and don't know what's going on, it's because they forgot this section and things like this. They forgot how to sketch in general in 2D. So you should know how to sketch a straight line, know how to sketch a parabola, know how to sketch general polynomials, know how to sketch circles, know how to sketch ellipses, know how to sketch hyperbolas. Yeah. So we are going to be focusing on the sketching. The things that I didn't say ignore, you should memorize. So you should know what the equation of a parabola and all that looks like. Know what the equation of a circle looks like. Also notice when you have one of these equations, but it's not in standard form, like we had with the circle earlier, where you know, oh, I'd have to move and complete the square to get it to be in a certain form. That being said, let's actually talk about the sketching. And at this point, I don't think I'll have time to go over the example. So I'll just show you guys how to sketch, the strategies for sketching ellipses and hyperbolas. And then you guys try these sketches for next time. I'll start the next class with sketching these guys, and we can move on to the next topic. So we're 15 minutes behind, so I'm not going to get to it. Okay, so sketching ellipses. So these guys look like x minus h squared over a squared plus y minus k squared over b squared equals 1. Specifically, always number 1. How to sketch? One, identify the center, h comma k. H comma k is the center. 2, from h comma k, move a units left and right, and b units up and down. Notice that the A is below the X and the B is below the Y. 3, this creates a rectangle. 4, the ellipse is inscribed. Now, those are just some shortcuts. They're not meant to be comprehensive, but if I actually draw it for you, you should be able to see what each of these steps are talking about. So let's say here, step 1, identify h comma k. So let's say my h comma k is right here. What I'm going to do is I'm going to move a units left and right. So I move a distance of A left and right. Then I'm going to move a distance of B up and down. Let's make this a little bit smaller. Notice that this creates a box, right? The B's the height is going to be given by 2 times the b, and the length is going to be given by 2 times the a. The ellipse is inscribed in this box. The ellipse is going to be the curve that passes through these 4 points. So that's how you'd sketch the ellipse. And hopefully there are no questions on that. Now, of course, if the A length is longer than the B length, your ellipse stretches horizontally. And if your B length is longer than the A length, your ellipse stretches vertically. And the guys who are on the longer length, those coordinates at the endpoints, those are called the vertices of the major axis. And the smaller length, those points are called the vertices of the minor axis. So the major and minor axis are labeled based on who's longer or who's smaller, based on the A and the B. Let's talk about sketching hyperbolas. So there are 2 varieties of hyperbolas. So you can have x minus h squared over a squared minus y minus k squared over b squared equals 1. Notice that you have a negative in the middle instead of a positive. And the second version is where the x is the one that's subtracted. You draw both at the same time. So how to sketch. One, again, locate the center. Two, very similar. Move A units left, right, and B units up, down. This creates a box. There's a part here that you have to do with hyperbolas that you don't have to do with ellipses. What you're going to do is you're going to extend the diagonals of the box forever in each direction. 5, if 1, as in this, hyperbola opens east-west. If 2, hyperbola opens north-south. The diagonals form asymptotes. What do I mean? So let's say sketch of 1. Just need a couple more minutes to get through this. Okay, so first you identify the HK. And as before, I use A equals green, B equals blue. A left, right, B up, down, you would create a box, which I did in red. And these are very faint lines. They're not a part of the graph. And now what you're going to do is you're going to extend the diagonals of this box. Those form the asymptotes. Now, if you are the first scenario where the x is positive, you extend east-west. So this is where your vertex is going to be, and you're going to extend, and you're going to be asymptotic to that. And then this guy going to be asymptotic to that. All right, so that's the sideways. And for 2, you essentially start out the same way, except on the very last step, you open north-south instead of east-west. So I identify the center HK. I move A units left and right. I move B units up and down. This creates a box. I extend the diagonals of this box. And when the y is positive, the vertices are on the vertical line, and they open up asymptotic to those lines. Okay, so that's just a quick crash course in sketching conic sections. I assume you all know how to sketch hyperbolas, parabolas, and circles, but hyperbolas and ellipses, people often forget how to sketch them because we don't do them as often. You need to remember how to sketch them. Yeah, so I know a lot of you have class soon, so we will stop there, but try these examples. I'll leave them in the notes for next time. And I will see you guys then. So thank you for your attention. Thanks for the participation. Threw out some good ideas today. I will see you all later, some of you later today. All right. Until then, I will see you guys in the next one. Ciao.